The math retreat is on Monday. So that means this class won't happen on Monday. In fact, no math classes will happen on Monday. Across the day, there will be lots of different math talks going on. I sent out a schedule. The other thing to point out is there is a math retreat competition in the afternoon/evening at, what, like 4:30, I think it is, 3:30? Something like that. It's in the schedule. If you sign up for it, you'll get some extra credit points. Any people planning on doing that? Okay. Noted. But no one says that I do not extend offers of extra credit that people want. There are also, prizes. There is a cash prize for the thing. It's not enough to be worthwhile incentive-wise, but there are prizes to be won. And as the organizer of the thing, maybe I can disclose the total registered contestant pool is not terribly large, so your chances of getting some prizes are not bad. Send me an email by this Saturday if you change your mind, and even if you don't have a team, I can assemble you into a team with some other people. Cool. So, let's talk about trigonometry. So right now we have a philosophy of trigonometry regarding right triangles. If you have a right triangle, and like an angle and a side, then you can figure out everything. In general, something much more strong is true about triangles. If you know 3 things about a triangle, you probably know that whole triangle. If you know, not that this is like 90 degrees, but maybe you know that's like 100 degrees, this side and this angle, then you know the triangle. Those are the techniques I'm going to start developing right now. And the first thing to talk about is the area formula for any triangle. So let's start building that. And it's built out of something reasonably straightforward. So there's a nice little triangle. What's the area of that triangle? 1/2 base times height, right? That triangle takes up half of the space in the base times height rectangle. So the area of any triangle is 1/2 times the size of the base times the height. But what if you're not directly given those pieces of information? What if you're, say, instead given this side and this side and this angle? Should you still be able to figure out the area? Oh yeah, I can do that. Thank you. I think, and as a strategy, let's start by trying to figure out what the height of this triangle is. So let's drop this perpendicular from this point. Is there now a right triangle you might take advantage of? Yeah, the pink one. So that pink one, let's label the height of this thing. That height is h, is exactly that pink side length that I dropped. Okay, so what's the area of this triangle? So I should address the font that's actually written. So what's the base of that triangle? How big is it? Or which variable name is assigned to the base?
C.
C. And so I have an area formula. The area of this thing is 1/2 times base times height. But I don't want to get a formula in terms of height. That's not one of the given pieces of information. So let's try to get a formula for that height by studying that pink right triangle. What trig function seems useful to find this height if you look at that triangle? Tangent could be used. Maybe there's a shortcoming. Do I know what that length is? Well, it's a piece of the side length C. It's not the whole thing. Sine, let's try sine. Do I know the hypotenuse? Do I want to find opposite? That sounds promising. So by looking at this triangle, it looks like I get sine of A equal to opposite h over hypotenuse B. That look like you could solve that for h? Yeah, what'd you get? Sine of A times B. H is sine of A times capital B. Oh, neat. So I could plug that in for the h in the formula above, right? So it looks like this area is 1/2 times C times the sine of A times B. Which, I don't know, that the symbols are just written in a weird order right now. Like B and C are similar things, so they should probably be next to each other. So maybe I'll just shuffle things around a little bit to get the area formula. If A and B are sides of a triangle meeting at an angle A, like this, then the area of that triangle is 1/2 B, C, sine of A. So whenever you see a triangle whose area you want to compute, if you know two sides and the angle at which they meet, you know the area. Does that feel pretty okay? Groovy. Let's use that on the next page. So here is a triangle. Maybe I'll remind you of the formula right here. So, there is a triangle. Do we know two sides and the angle at which they meet? Yeah, so we should be able to use this area formula to write down the area. So according to the area formula, what is the area of this triangle?
It would be 1/2 times 4 times 2 times the sine.
Yeah, if we actually cared about that number, we would probably want to simplify that sum. So let's go ahead and simplify. What's the sine of pi over 8? Square root 2 minus square root 2 all over 2. Even if that's not a number that you, like, just remember, now that it's written down, you remember doing it though, right? Or talking about it, saying that that's true without saying why. Yeah, so let's put that in. So there's 1/2 times 4 times 2 times the square root of 2 minus the square root of 2 all over 2. Should any simplification be done at this point? Any cancellation? Yeah, the 2's, right? I see a 4 in the numerator and I divide by 2 twice. So it sure looks like this resulting area is 2 times the square root of 2 minus the square root of 2. And I guess if we wanted a decimal approximation, at this point we'd resort to a machine. How many people have just already done that? Let's do it. I'll pull up my forward calculator to use. 2 times the square root of 2 minus the square root of 2, close parentheses. Check the spelling. Somewhere around 1.5? Cool. How do people feel about that application? Oh, maybe we should check this. Are the side lengths given with any units? No, okay, so we can't put any units in the answer. Those are just abstract numbers, no units inside. Ooh. So there's formula one of the day, the area formula. The more important formula to me that I want to say is the so-called law of sines, which is a way of taking this idea that you know 3 facts and you can find out everything about the triangle and putting it into it. And the key to it is, if you look at that triangle I used up there, could I just as well have used, I don't know, I guess this would be the side length B, that would be the side length A. Could I use these 3 to compute the area? And I better get the same result. If that angle's little c, could I use those 3 to compute the area? Yeah, so there are 3 different ways to compute the area. They all have to give the same result. Let's see what that tells us. So let's take this triangle. Side lengths A, B, and C, angles opposite called A, B, and C. And let's compute the area of this thing 3 different ways. So if you use these 3, you'll get 1/2 BC times the sine of A, giving the area of the triangle. What if you use these 3? What do you get then? Well, the formula will be the same, right? It's 1/2 times the product of 2 sides. So which 2 sides do I want to think about right now? A and C. Times the angle at which they meet, the sine of the angle at which they meet. What's the angle at which they meet? Cool. And I could do the same a third way. If I use those 3, I'll get 1/2 AB sine of C. And all 3 of those things have to be the exact same. So let's take 2 of them, set them equal to each other, see what happens. Maybe I'll take the 2 on the left because those are the 2 on the left. So apparently then, 1/2 BC sine of A is equal to 1/2 AC sine of B. And let's just try to simplify that. And let's also have and try to get this into a form that's solved somehow like alphabetically. So all the A's are on one side, all the B's are on the other. Not that that's like objectively a correct thing to do, but it'll be something that gives us something in a nice way. So let's take this and try to simplify it. Is there anything you could, that appears on both sides of that equal sign that you could cancel? 1/2 and C. You're both right. Just come on. So by canceling 1/2 C from both sides, what are we left with? We're left with B sine A is equal to A sine B. And if we want to get all the A's onto one side and all the B's onto the other side, well, I just think there's some division that needs to happen. Would you rather see the sides in the denominator or the signs in the denominator? Folks, for the signs should be in the denominator. Folks, for the sides should be in the denominator. Okay, I wasn't expecting that to be so strongly one way or the other. So, I guess I'll divide by big B and big A. Right, cross divide. So we wind up with sine of little a divided by big A is equal to sine of little b over big B. That's 2/3 of the law of sines. The law of sines says that the sine of A over A is equal to the sine of B over B. So going back to the top picture, what does that say? That says if you take a pair consisting of an angle and the side opposite, and another pair consisting of an angle and the side opposite, those ratios should be the same? Do you think we could do the same thing to get c's into the mix? Yeah. And maybe I'll write down the starting line and see if people want to do it. Right? This should be equal to that. 1/2 AC sine B should be equal to 1/2 AB sine C. And I'll try to be consistent today about drawing my little c's like lowercase c's, like cursive c's, just to make sure that they're really different from my capital c's. So I'm not using like a special character called tidal wave. It's supposed to be a cursive c. If we go and solve that, do you think we'll get something pretty similar to what we got in the first column? Do people want to go through the algebra? Cool. I guess many of you probably already have at the time that I've been solving. So I'll jump to the conclusion. You'll wind up with something really similar. Sine of little b over big B is equal to sine of little c over big C. Well, hey, look, that's the same thing as we got in this term is the same. So all of the law of sines says that this is also equal to that. I feel pretty okay. So, like you told me you wanted the sides to be in the denominator, but sometimes it's more useful to see them in the numerator. Can I take the reciprocal of every one of these and still have equality? Yeah. So I'll put that down also, just because that's another useful way to think sometimes. A over the sine of A is equal to B over the sine of B is equal to C over the sine of C. So that's what the law of sines says. And I said that this is a tool you can use when you know 3 facts about a triangle to find the other 3 facts. Well, I'm imagining a triangle is like the 6 facts about a triangle are the 3 sides and the 3 angles. Let's see that in practice. Here is a triangle. Let's suppose you encounter a triangle, not drawn to scale, which has 2 angles, a 20-degree angle and a 10-degree angle, and the side length between them is 3. That's not on the screen. Let's try to use this and the law of sines to determine everything about this triangle. I guess what's one thing that is obvious that you could use about this triangle that isn't already the triangle. What do the 3 angles of a triangle have to add up to? 180 degrees, and this is a problem with degrees, so it's appropriate to talk in degrees. I'm not going to go on quite to and say it's pi radians this time. So let's use that to find C. C plus 10 degrees plus 20 degrees is 180 degrees. So tell me, what is C? 150 degrees. All right, now let's take advantage of the law of sines. Is there a pair consisting of an angle and a side opposite that I know? Cool. So the law of sines says that the ratio of side to angle opposite is the same no matter which one I choose. And I'd like to know side length, so I think I'll use the one that has a side length in the numerator. So let's use that. The law of sines. So I'll focus on B. I'll try to find B. Says that B over sine of 20 degrees is equal to 3 over sine of 150 degrees. Does that look like something you could solve for b? Yeah, just multiply the thing to the other side. So it looks like b is in fact equal to 3 times the sine of 20 degrees over the sine of 150 degrees. And maybe before you reach for your calculator, which you will reach for in a second, you should ask yourself, are those angles that are just angles whose sines and cosines you're supposed to know already? Yeah, I know 40 degrees, 45 degrees, and 60 degrees. This isn't one of them, so calculator is the best strategy I have. Of the people who have already resorted to a machine, what does it look like the side length b is? (2.1)? Cool. Does that agree? Do you think something similar could be done to find the side length c? Yeah, I bet. And maybe I'll give the 3 options that I like to give about this. No, I think I'll just give 2. I can talk through it, or you can just do it and then we'll come together. People want me to talk through one more example of the same problem? All right, take a moment, find the side length c.
We're doing C or A?
The one that we don't know already.
So A.
Yeah, there is no side length c in this.
Okay.
Yeah, this one. Once you have an answer, you want to just compare it with those around you.
But it should be the same. Yeah, I don't
Cool. What is this side length equal to? I hold a 1. Surely it's not exact now.
Yeah.
Okay. So that was the approximate value. What was the exact?
3 times sine of 10 degrees over sine.
Nice. Cool. People get consistent answers with that? Anyone want to see talked about? Awesome. So there's the optimal case for using the law of sines. If you know 2 angles, then you can find the third angle immediately. And then, well, if you know a side length, you can use the law of sines as the ratio that you can multiply by to find all of the other side lengths. Brilliant. So there's one other situation that law of sines is the right tool to use. And let's see some examples of that. Let's suppose that you know this kind of information. So here is another triangle worth studying. Let's suppose you have a triangle, you have a side length of 3, a side length of 4, and the angle not between them is 60 degrees. Let's try to find everything about this triangle. So I guess, first things first, do I know two of the angles already? No. So I can't just use the two angles have to add up to 180 degrees. I get some relationship like a plus c plus 60 equals 180, so I guess a plus c is 120, but that doesn't help. So let's try to jump right to the law of sines. Do I know a pair consisting of a side length and an angle opposite? Nice. So I know these two things. Is there another side length that I know? Yeah, I know the side length 4. So let's use that. It looks like this time I'm going to try to find an angle. So let's have the sine of the angle be the thing in the numerator this time. So let's try to walk this out this way. So apparently, sine of c divided by 4 is equal to the sine of 60 degrees divided by 3. So far, so good? All right, let's try to just think on that and see what we can see. So you want to solve that for c. So maybe it's a good first step to just solve that for the sine of c. All right, so looking at that, what's the sine of c equal to? 4 times the sine of 60 degrees over 3. All right, just cross multiply. Maybe before we proceed, the sine of 60 degrees, is that a number that you know? By looking at your units also? That's 45 degrees. Root 3 over 2. And that's not something that like I expect you to have at the top of your head all the time, but you have that units all something like that. I guess it's only written down in radians the one I gave you. But okay, cool. Root 3 over 3. So 4 root 3 over 2, then divide by 3 again. That looks like it's 2 root 3 over 3. So right now we have the sine of c is equal to 2 root 3 over 3. So, I guess we can check one thing before we proceed much further. What is 2 root 3 over 3 approximately? This is a machine-y kind of problem. Oh, that's a problem. Cool. This problem is going to be less interesting. Well, interesting for a different reason than I want to emphasize. How many angles are there whose sine is 1.15? None. Are there any values for c which satisfy that equation? Sine of c is never greater than 1. No such c exists. So we can jump to a conclusion. There are no triangles in existence which satisfy these conditions. How do people feel about that? I feel a little bit unsatisfied, so I'm going to tweak the example a little bit right now. I'm going to move to some of the space at the bottom of the page, and we'll talk through a similar problem, which will have a number of solutions, which is interesting for a different reason. So, let's try this. So here is a triangle that's going to look quite similar. 4, 3, A, C. Let's make this 30 degrees this time. Yes. So let's try to go through the same sort of motions to solve this problem. Trouble is, I'm going to take myself into a corner real quick. I don't want to go like right onto the board because you have the note sheets that are supposed to be the space for everything that I write. So let's do it. Do I know a pair consisting of an angle and a side opposite? Is there another side that I know? So I should be able to find the sine of the angle opposite. Let's go ahead and do that. It'll be real quick because it's the exact same step walk as we just did, right? So, it looks like sine of C over 4 is equal to sine 30 degrees over 3. And let's simplify this right now. What's the sine of 30 degrees? No, that was 60 degrees. 1/2. So I guess that's 1 over 2 over 3, also known as 1 over 6. I would like to know what C is, so first I'll multiply that 4 over to the other side. Sine of C is equal to 4 over 6 is 2 over 3. Is that quantity now less than 1? Or alternately, there's some muttering. Have I done anything silly? Or just wrong?
We're just confused like what happened to the 4, but then you put it back into the multiply by 4.
Oh yeah, so this is, that's that one. So all of these things are the same. I'm just simplifying to you right-hand side. Nice. Alright, so I know that the sine of C is equal to 2 thirds. And that angle C, it's an angle in a triangle. So it's an angle that's somewhere between 0 and 180 degrees. How many angles between 0 and 180 degrees have sine equal to 2 thirds? Notice I'm not asking what they are, I'm just asking how many are there. And let's draw a picture of it. So let's see, from the unit circle point of view, sine, is that the x value or the y value? Y value. And I'm interested in an angle between 0 and 180. So an angle in this range, because that's the biggest angle I can see in a triangle. Well, I can't actually get to 180. The angles I see in a triangle are between 0 and 180 degrees. And I want sine to be 2 thirds. So I'll draw a line at y equals 2 thirds. How many angles are there that produce a sine of 2 over 3? 2 of them. This one and this one. They're the 2 angles that I want to find. One of them we already have a name for. What is the angle in quadrant 1 whose sine is 2 thirds? What undoes sine? Arc sine, or inverse sine, or sine inverse. So there's one angle. One choice of C is sine inverse of 2 over 3, which we can approximate in a moment. How about the other one? How does this angle align with that angle? Not plus pi over 2. I want to reflect over the y-axis. So instead of rotating up, I want to go all the way to 180 degrees and then go back. So 180 degrees minus whatever that angle is. Whew. All right, so let's approximate those. Let's do it. So doing it using the machine that I like to use, arc sine of 2 over 3. It claims to be about 7.3 radians. Do we want to answer in radians in this problem now? No, other things are in degrees. Let's walk in degrees. So I guess the two tricks would be either say I would like my answer in degrees, so putting your calculator in degree mode would be analogous to that. If you didn't know how to do that, then I guess you would just multiply by 180 over pi.
You're doing it in arc cosine. Yeah.
Ah.
Okay.
I think that was an autocorrect issue. I hope. All right, and it still says radians, but I've multiplied by 180 and divided by pi, so that is in fact in degrees. Gives me, I'm just going to write that number down, approximately 42 degrees. Or I want 180 minus that. Oh, so this one you won't do, huh? Nope, okay. That's the trouble with not using an actual calculator. Of course, in this time, any of you that are actually using a machine already have their answer. And in fact, that again is still long. One of those is in radians. What is that using your machine?
About 138.
About 138. And in degrees. So let's notice something about these two angles. That angle, 42 degrees, is an acute angle. It's less than a right angle. The angle 142 degrees is obtuse. So the law of sines will always predict these two answers, except when it predicts no answers. One will be acute, one will be obtuse. And let's just look at this example and see if it would even maybe make sense for the side C to possibly be obtuse. So if that angle C is obtuse, it's the biggest angle, so it has to be opposite the biggest side length. Is it possible that that is the biggest side length? Yeah. So both of those are valid solutions. Given I know those two answers, do you think you could find A? Once you know A, B, and C, and 3, and 4, do you think you could find the third side using the law of sines again? Yeah. Nice. So there are going to be two solutions. You can completely find those two solutions. Let's do one last example in which a different sort of subtlety happens. Let's try to address this angle side problem. Is this just going to be worse? No, that'll be fine. So let's try to solve that triangle by going through the same motions. So first things first, do I know a pair consisting of a side and an angle opposite? Yeah. So I'm set up to use the law of sines to figure out this side length. So apparently the sine of C over 3 is equal to the sine of 60 degrees all over 4. All right, what do I get? I guess I'll get 3 root 3 over 2 all over 4, also known as 3 root 3 over 8, I think. So there's what the sine of C is. Nope, I haven't divided by 3 yet. No, I have. Christ, what are you doing? All right, there we go. Questions right now? Have I done anything silly or that doesn't make sense? All right, so there's the sine of C. How many angles are there that result in that for sine? In between 0 and 180? 2. So let's write the 2 of them down. One choice is the inverse sine, or arc sine, or whichever you prefer, of 3 root 3 over 8, or (180 degrees minus). And let's decorate these two. So this one is acute. This option is obtuse. And let's check out this triangle. So that angle C, we're seeing one option for C, which might be obtuse. If that angle is obtuse, then the side opposite must be the biggest angle. Is the side opposite C the biggest angle? So is C allowed to be obtuse? Are both of those acceptable values for C? No. So maybe I'll put this in a sentence written down. Since the side opposite C is not the longest, C cannot be, that's a terrible bit of handwriting. Cannot be obtuse. So C must be equal to the inverse sine of 3 root 3 over 8. And what is 3 root 3 over 8 approximately? I assume someone's plugged that into a calculator by now.
40.5.
Groovy. And with a number that size, I'm talking you're in degree mode. Nice. All right. So let's go through the motions of finding the angle little a at least. So now that we know the angle C, how can we find the angle A? What do the angles of the triangle have to add up to? 180. Do I know all but one of those? I should be able to solve for the last one. All right, so I guess this is going to go right there. So apparently 180 degrees minus 60 degrees minus the inverse sine of 3 root 3 over 8. Well, that will be equal to the angle A. So let's compute the angle A, and I guess we're going to jump straight to an approximation right now. All right, so it'll be 180 minus 60 minus the arc sine of 3 times the square root of 3 over 2. And you all know how to convert your calculator into degree mode. I can't do that so reliably, but I know how to convert from radians to degrees. I'll multiply by 180 over pi. Cool. not over 2 over 8. Right, so Wolfram alpha is perfectly happy being clever, and if you plug in a number whose arc sign doesn't exist, it just says, well, I know how to make sense of it if I'm allowed complex numbers. It was just giving me an imaginary angle that this had to be. So, it looks like this works out to be 79.5 degrees-ish. Does that agree with what people got on their own? Nice, then I think I believe it. Cool. Does that feel pretty okay? So, I think with my own 4 minutes, maybe I'll go through a broad stroke strategy description of what this says. So let's suppose that you encounter yourself a triangle problem that you need to solve. So a situation where you know 3 things about a triangle. So you have some sides, maybe you know some of them, you have some angles. You know some of them. As long as you know 3 of them, you should be able to basically work out what the triangle is. Unless you just know all 3 angles. If you know all 3 angles, then you can like scale the triangle all you want. So you don't actually know any of the side lines. So if you know all 3 angles, you still know enough information. If you know 2 angles and a side, or if you know 2 angles, you can find the 3rd angle. You can use the law of sines to find those sides. And that's like the first example we did was pretty straightforward. If you have a side-side angle triangle, so you know 2 sides and then the angle that follows them, then you have enough information to make progress. You can use the law of sines to find sine of an angle, then use inverse sine to find that angle. There might be 2 angles, maybe none. If there's no such angle, then you're done already. Because I don't think there's not even a choice of angles. See that makes this triangle walk. This isn't a triangle. Once you know the 2, you apply the 4th angle, use the law of sines to get the 4th side. And maybe let's just go through. So there are 2 other situations you might have. You might know 2 sides and the angle at which they meet. It's like the situation of the area formula, in fact. That's not that you're not in a place where you can use the law of sines. There will be a tool we will next time called the law of cosine that will help. If you know all 3 sides, you can find all the angles by the law of cosines, which you get on the next time. So let's talk through the detailed guide for the side-side angle triangles. So if you find yourself in a side-side angle situation, here's a flowchart. First, locate the known, the angle and known side opposites. So in this case, you know that A, you know that little a. Locate an angle B that is opposite a known side, big B. You can use the law of sines to write down this equation, where here, this B right now is unknown, and all of these are known. And you can solve that for B. What are you doing, Chris? Cool. So now here's where the 3 pieces come in. Does this say that sine of B is something that's bigger than 1? If it does, then there are no solutions. Sine of B can never be bigger than 1. Otherwise, if B is not the longest side length, if this side is not the longest side length, then the angle little b must be acute. And so you just get inverse sine of this. If the side length B is bigger than side length A, then side length B might be the biggest side length. So then there are 2 choices. Either it's sine inverse of the thing in blue, or it's pi minus the inverse sine of the thing in blue. Or 180 degrees minus the same thing, if you're walking in degrees. Once you know all those two angles, you can find the angle C. Once you know all the angles, you can find the remaining side. Cool. And at least that high. All right, so on Monday is the math retreat. Join, in fact, I think my very class time, there is someone from the National Institute of Standards and Technology, Angela Robinson, who is a expert on cryptography, who will be talking about cryptography. And also, I think a little bit about my training at the National Institute of Standards and Technology. Oh, thank you. Whew.